What is the value of I, the imaginary number, raised to the power of itself? The first thing that we notice about this expression is the I in the exponent. And how can we deal with this? First of all, we want to apply this identity. X is equal to e to the power of ln x. We can treat I to the I as x to give us this. A very useful property of logarithms is bringing down the exponent, like this. If we apply this formula, we will get e to the power of I ln I, so I to the I is equal to e to the I ln I. Now the problem becomes working out ln I. But to do this, let's take a step back and derive a formula. This is the complex plane, and this is a complex number. It's made out of two parts, a and bi. But let's convert it to polar coordinates. So instead of using a and b, we can use r and theta, where r is the radius from the origin to the point, and theta is the angle up to the radius from the x-axis. Using normal trigonometry, we can see a as r cosine theta, and b as r sine theta. Since z is a plus bi, we can substitute into z, meaning we switch out a for r cosine theta, and b for r sine theta. Z now becomes r cosine theta plus ri sine theta. We can factor out the r and then apply Euler's formula. This further compacts z to simply re to the I theta. Now what we do is take the natural log of both sides, giving us ln z is equal to ln r e to the I theta. We can apply this property of logarithms to split out the right hand side. But ln e is simply 1, so we can cancel it out. And we obtain our formula. ln z is equal to ln r plus I theta. This is our first expression and the formula we just worked out. We want to work out ln I, so let's set z equal to I. So let's work out r and theta. This is the point I on the complex plane. It's a distance of 1 from the origin, giving us r is equal to 1. Similarly, it's a right angle above the x-axis, giving us that theta is pi over 2 radians. We can now substitute all of these values into the formula. This will give us ln I is equal to ln 1 plus I times pi over 2. ln 1 is 0, so we can cancel it. And now we can substitute for ln I into the first expression, switching out the ln I for I times pi over 2. This will give us e to the power of I times pi over 2, giving us I squared. By definition, I squared is negative 1, so we have e to the power of negative pi over 2. This is roughly equal to 0.2078 and so on. And this is a completely real number. But is this the only solution? And I'll tell you straight away that it's not. And not only that, there are infinitely many more solutions. So let's see how to find all of these. To do that, let's come back to the complex plane. When we plotted I, we found that r is equal to 1 because it's a distance of 1 from the origin. Also, it's a right angle above the x-axis, so we saw that theta is pi by 2. R is equal to 1 is perfectly correct. It truly is a distance of 1 from the origin. But theta is equal to pi over 2 is not the only angle that can work here. Because notice, you could go around a full circle to get back to the same angle. Meaning we can take another 2 pi radians around the circle to get to the same angle, or in this case 5 pi over 2. In fact, we can take away or add 2 pi to get to the same angle as many times as we like. So theta is equal to pi over 2 plus 2 pi times some number, n. But since I to the power of I is equal to e to the power of negative theta, we know theta now, so we can substitute it in. So we have I to the power of I is equal to e to the power of negative pi over 2 plus 2 pi n. And you can plug in any value of n to give you any solution.